Next we come to another important circuit, which is just the reverse of decoder. Till now we have looked into comparators, right, as well as half addition circuit using XOR gates. After decoder, as you see this pipeline, we have n bits, right, and then you are trying to use those n bits to decode one of the 2 to the power n outputs, right. That is what was decoder. Encoder is actually takes that encoded output, right. It's basically you have 2 to the power n different inputs here, and it actually encodes it. Okay, so it's the other way around. It basically finds out which is the bit combination that we are trying to look for. Okay, so that is useful in different contexts, right. So it could be that you are choosing some kind of a level, right. So you want to, maybe you have a let's say a motor, right, and you want to either run it at a speed of either, so this is high speed, let's say, this is a medium speed, right, this is a slow speed, right, and let's say this is off. Okay, you select one of them, and it is encoded in some bit patterns, right, either, yeah, maybe this one is 1 1 high speed, this is 1 0 which is medium speed, 0 1 which is slow speed, 0 0 which is off, right, and this information is actually reflected here, and it goes to some kind of a digital circuit. Okay, and now you can, maybe they put like, maybe this 1 1 is directly converted into some kind of voltage, the fan speed increases, 1 1 which is 3 is more than 1 0 which is 2, is more than 0 1 which is 1, more than 0 0. So you can come up with some kind of argument for that. You can, let's say I want to control the speed of the motor using this encoder, right. So as a matter of the fact, all you need to know is that you have to choose one of these inputs, and you are going to also choose the appropriate bit combination, right. So here remember that you are not choosing one of this n, it is actually telling you the bits, right. There are n bits. Okay, so it is going to give you the bit pattern output. Okay, bit pattern is going to be the output. If it is, let's say, let me write it here, 0 1 2 3 4 5 6 7, right. So there are 8 bits here, so that is what is like 8 bits, 8 inputs rather. You can encode that using 3 bits. 2 to the power 3 is equal to 8, right. Here you have 3 bits, that's why you get 8 outputs, 8 outputs. So if you choose, let's say 5, right. So I am asking the encoder, please tell me the encoded version. So this 5 is basically the 5th line, okay, or the 6th line. This is going to tell you, okay, 5 is encoded as 101 in my system. Okay, so you can design, like, it does not have to be that the 5th line has to map with 101. This is how our convention is, but any sort of inputs can be encoded, right, to a specific bit pattern that I wish, right, that I want to encode it in that particular form. That particular line has to be encoded with that particular form, right. So you can have 2 to the power n different inputs, and you can have these n outputs. Okay, so here is another example. Here I am trying to show that if you have a 4:2 encoder, you can have these inputs, as I kind of already showed you. Here I am choosing one of them. Note that you are choosing only one of them, that you are not choosing all of them, right. Only one is going to be entertained, because there is that particular input has to be encoded. So what I am saying is that the input is encoded. I would say input line. Okay, so only one input. Okay, I would say is anticipated. Or expected, right. So, you are expecting only one input and you want to know the corresponding bit pattern on the output. So, here if I want to choose the 0th input, the bit pattern is this. If I do the first input, the input pattern is this. If I choose this one, it will be this. If I choose this one, it will be this. Don't think that I am forced to make this choice of these bit patterns, right. It could be also that 0 0 0 1 I might require a different bit pattern. That doesn't matter. I mean, that is not going to create any issue, right. It is still a decoder, it's still an encoder, but it's a different encoder. It is you have defined your own encoder. So, this is something that you will again logically find out, right. So, you can see here, if you look at y1, if I find out what are the terms that appear in y1, you can see very easily that y1 is basically 1. It does not actually depend on L1 and L0 at all, right. So, these are all zeros, right. It depends on if L2 is 1 or L3 is 1. Okay, you can try this out, simplify, but from common sense you can observe, right. Y1 is 1 when either L2 is 1, see, or L1, L3 is 1. So, you can take L2 and L3, put them through an OR gate and that is Y1, right. Similarly, if you look at Y0, let me use a different color. Y0, you can see this is 1 and this is 1. When L1 has to be 1, then it is 1, I could see, or L3 has to be 1, right. So, I can again take L3 and L1 and put them through this OR gate and put it out as Y0. Okay, this is a circuit design. Suppose I want the other way around, right. I might want some other combination. I will just tell you, let me let me kind of take some space on the top, right. Say for that 0 0 0 1, I want y1 y0, so 0 0 1 0 0 1 0 0 1 0 0 0. So, these are the expected inputs, right, but nobody tells us that it 0 0 0 1 has to be 0 0, right. This could be 0 1, right, this could be 1 0, this could be 1 1 and this could be, let us say, 0 0, for whatever requirement, I do not care. Okay, you can always come up with a circuit for this. It is going to be different. This encoder, whatever is the standard definition, you can change it, because it is, you are trying to design your own encoding circuit. Okay, encoder's essence is that you are encoding the input to some output. Okay, it's just some kind of an ordering of the bits, right, that kind of matter. Okay, but the common common way to do this is whatever I have shown you. That doesn't matter. That is what I think you need to kind of carry forward from this discussion. There is one more concept, as I told you, that input line is encoded and only one input is anticipated, but there could be other kind of use cases where there might be multiple inputs. Okay, so what if, because this inputs to the encoder might come from different sources and you might want to, you can only output one bit pattern, right, to some input, right. So, let us say this is your encoder circuit, this is your encoder circuit, these are all your inputs and this is your output, right. So, by definition, in your output you can only encode one of the inputs, you cannot encode multiple inputs. That does not make any sense, right. Suppose you are encoding 1 0 1 0 1, right. So, this actually is going to correspond to very specific, let us say this is your most significant bit, right. So, then it makes 16 plus 5 21. So, it is some probably 21st input is going to be entertained, right. This means that somebody has inputted 21, but suppose you want to choose both of them or multiple ones, right, or more than one. Say this is activated, sorry, this is activated this is activated, and also this is activated. What should you do? You cannot output 3 different bit patterns, right? Because if this is a 1, 2, 3, 4, 5, 6, right, 6 bits, right, or 5, whatever number of bits, right, whatever the bit pattern that you are generating corresponds to only single line here, right. So in case you have multiple such things, you can actually give a priority, right, and don't care about the other one. Suppose in this particular case, I have this A, B, C, D and E as these inputs, and the priority is that A has the highest priority, B has the second highest priority, and so on. So if A is chosen, I don't care whether B, C, D and E are chosen. So that is why I represent that with an X, which is called a don't care condition in the truth table. Okay, 0 and 1 is already kind of discussed, and you know 0 means you are not choosing or that particular logic is false. If 1 is chosen, it is true. But there is this thing called X, which is I don't care whether it's 1 or 0. It could be 1, it could be 0. Your circuit behavior should not depend on X being 1 or X being 0. That is extremely important. Your circuit behavior is agnostic to don't care conditions, So I don't care. So for example, let's say L3, L2, L1, L0. If L3 is chosen, I give the highest priority. If L3 is chosen, the corresponding output should be 1, 1, right, and 1, 1 is given priority, right, because even if somebody chooses L2 or L1, it doesn't matter. Okay, so let's say look at the other one. If L3 is 0, L2 is 1, and these things become don't care, because 2 has the higher priority than 1 and 0. Similarly, 1 has a higher priority than 0, and if this one is chosen, so it could also have 0, 0, 0, 0, nothing is chosen. So the output could be 0, 0 also, and you can have one more output called none, right, which is means that nothing is chosen. That is also a possible thing that may happen. Okay, so what is Y1 here? Y1 is going to be turned on when if L3 is 1, but L3 is 1, then you don't have to look at any other variables. Okay, I am trying to tell you how you can logically even write these equations without doing the formality of going through mean terms and so on. Y1 is going to be chosen if L3 is 1, that is the highest priority. I don't even have to talk to anybody else. Okay, so L3, or I can choose if L2 is 1, but I need to make sure that L3 is not 1, right. So I can also have this thing called L3 bar L2. That means L2 is true, right, but I am not I am also making sure that at the same time L3 is not true. So the contribution of this term is going to come from L2 only if L3 is off, which you can simplify as L3 plus L2, because logically if you simplify what I said, this basically means if L3 is on or L2 is on, doesn't matter, you can turn Y1 on, and you can find it very easily here also. Okay, so Y1 is going to be L2 plus L3. For Y0 is going to be on for L3, because L3 requires both of them to be 1. So if L3 is 1, I don't even have to think, right, L3 must be there. The other condition when Y0 is on is L1, but I need to make sure that these two are off. This has to be off, this has to be off. Only in that condition I am going to take that L1 is equal to 1. Okay, so I am going to use L3 plus the other condition is L1, but need to make sure that these two are off. Okay, which gets simplified to L3 plus L2 bar L1. Okay, so these are the two outputs, right. You can always populate the truth table and find it out. It will come to the same, it's an exercise. It's just going to be a larger truth table, because you have 4 different inputs, and if you consider multiple inputs to be activated at the same time, you are going to have 2 to the power 4 different rows, right, 16 rows, and they will cover all the don't care conditions, because in this particular case, see, this could be 0 or 1, right, this could be 0 or 1, this could be 0 or 1, right. This itself has 8 cases, right, 2 multiplied by 2 multiplied by 2, all of them are going to have L3 is equal to 1, so that I don't care, y1 and y0, both of them are going to have L3 term. Okay, you are encouraged to expand this don't care condition in both ones and zeros and solve the same problem, and just kind of justify it to yourself that they are logically equivalent. The equations are going to be exactly the same. Okay. So the next circuit that I want to talk about is called a multiplexer. It's another very important circuit which controls the flow of a certain input to the output. Okay, earlier it was more about mapping. Okay, mapping multiple inputs, n bits, right? N bits are going to be choosing one of the outputs. Okay, 2 to the power n outputs. That is called a decoder, right? Here the encoder was that there was 2 to the power n different inputs. Expectedly one of them is going to be turned on, and you want to see the bit pattern of that. Multiplexer differs from them a little bit. Here you have some inputs and you want to channelize the same input to the output, right. So it is like I am giving you this analogy of this this cable TV, right. Let us say this your set top box. This is just an analogy, by the way, right. So you have these n channels, right. You have Doordarshan, you have some Z, you have some Star Sports, or all these things, right. And your output is either one of them based on which one you want to channelize, right. If you want to watch Doordarshan, you just say I want to see channel 0. So this will be selected and you can see here DD, right. Then you say no, I want to see some Star Sports, right. Then this will be selected, but then the output is not going to be DD anymore, right. The output is going to be some star. Okay. So similarly here I have some inputs. If you think of this as a multiplexer, the multiplexer is going to have this number of inputs and it is going to take one of those inputs to the output. Okay. And which one has to go? This is controlled by something called select lines. You have the TV remote which probably sends instructions to the set top box. If there is an input, right, which basically says select. Okay, select lines choose. You have to tell the set top box which line to choose or which channel to choose. Somebody has to tell, right. So in a multiplexer also, this S is known as the select line. Okay. So it selects one of the n inputs to connect to the output, and you need log n to the base 2 bits as the control input, because if you want to choose one of these channels, right, suppose you have n channels, you can choose this using a bit pattern here, which is log n to the base 2, right. Basically if you have 3 select lines, you can choose from 8 different channels. Okay, this is another way of saying this, right. So this is your encoded channel number. Okay, 101 if you say, this is going to select the 5th line. If you say 111, this is going to select the 7th line, and so on, right. If you say 000, it is going to select the 0th line, like that. Okay, so the select line need not always be just a bit, right. It is a very simple multiplexer that I have shown here, 2:1 mux. But this S could be multi-bit, and based on that you have to, the circuit will become much more complex. It could be a 4:1 mux, or it could be a 8:1 mux, right. So you can see the general functioning of how this circuit works. A and B are the inputs, but I have to control who goes to the output, right. So, suppose I select S is equal to 0, right. If I select S is equal to 0, immediately this is switched off, right. So, 0 means this is switched off, this is going to be 0, nothing is going to come out, right. Irrespective of the value of B, this is going to be 0, irrespective of the value of B, does not matter if B is 1 or B is 0, does not matter, right. Now, if it is 0, this makes it 1, right, because A bar, sorry, S bar. So, this is S bar is going to happen here. So, this is 1. So, I, by the virtue of my select line, I am not causing any problem to what comes to as C. Now, if A is equal to 0, right, you can see that the output is A is going to be 0 here. So, the output is 0. Does not matter what is the value of B, does not matter. B could be 0, B could be 1, it will still be 0, which is equal to A. If A is 1, then this is 1, right, this will be 1, and then this one is also going to be 1, which is A. Again, does not matter what is the value of B. Okay. However, if you choose the other way around, suppose you choose S is equal to 1, if S is equal to is 1, then S bar is equal to 0. So, you are switching it off. Okay. So, by default this output is going to become 0, right. So, then you can see by the same analogy that this is going to be 1, this is going to kind of reflect the value of B irrespective of the value of A. Okay. If S is equal to 1, if B is 1, let us say, 1 is going to come here and this is going to be 1 because OR is being fed 1 and this is equal to B, does not matter what the value of A is. Similarly, if you have B is equal to 0, this will be 0, this will be 0, output is going to be 0, yes. Okay. So, it is a way you can select some lines and give an output. Okay. This also has a huge number of not lot of functionalities, right. You want to channelize certain inputs, right. So, you do not want to input everything to a system, right. So, suppose you have some mechanism in about selecting some inputs. Okay. So, let us say the first input and the fifth input has to be chosen and added. So, those kind of things can be controlled by the select lines of the multiplexer. Okay. Or you can have the various devices, right, connected to the system. You want a particular device's output, right. So, those can be, or you want to write to a particular device, right. So, what read or write to a particular device. So, this could also be done using a multiplexer. You want to select one of the devices from k devices and from that you are reading. So, that is going to be multiplexed. Okay. So, it's just to show you, this could be input number 1, input number 2, this could be devices that will send you data, right, input number k, and this entire set of inputs could go to a mux, right. So, k is to 1 mux, right, and you have the output ready and this output is basically one of the k inputs, and here you have the number of selection lines is log k to the base 2. Okay. Now, you can control which device you want to talk to, right, or you want to read or write from. Okay. So, writing requires this other direction, right, called a demultiplexer, like a decoder. So, if you want the other way around, that is also possible, but that is a demux. Okay. So, you can try out bigger versions of multiplexers, let us say 4:1 and so on. So, the output C is always connected to either A or the input B. The output value depends on the value of the select line that I have already told you, right. And this one small task that you can try out. So, draw the schematic of a, you can also do 4:1, right, 4:1 or 8:1 mux. So, the first task is that you can try to do it in a raw form that I had been showing you here, right, just using NOT gates, AND gates and OR gates. and so combination of the basic and or not gates. The second thing is we are talking about creating complex modules from simple modules, right? That was something that I told you in the first class, right? So suppose you can create this 2:1 muxes. These are your Lego blocks, right? So these are your Lego blocks, right? 2:1 mux. So can you use only 2:1 2:1 muxes to build more complicated muxes? For example, here I have asked you to do a 8:1 mux. Okay, so how will you combine them to create bigger circuits, right? So this is another important thing that we need to know. Sometimes, as I told you, that not every circuit can be designed from scratch. You might be using existing functionalities and club them together to make more complicated circuits. Okay, so this is a very important exercise that you should be trying to do. So your block is, the first one should be simple, because given the pattern that I have already shown you, you should be able to say that, okay, how can I do a 8:1 mux? It requires 3 input lines, by the way. So instead of S, we are going to have for this thing, right? Select lines is going to have 3 things: S2, S1 and S0, right? Because we are choosing from 8, right? But that is one case. The other thing is that how do you want to not build the entire circuit from scratch, but you want to use this 2:1 muxes, right? So you want to use them and some combination of them to somehow realize this big black box, which is an 8:1 mux. This has one output and 8 inputs, 0, 1, 2, 7. Okay, so this is a very important exercise. Just try to see that how can you manage to do that. We can discuss some more problems like this in your practice assignments and so on, right?